Okay, so I want to go over the main things that we've done so far in terms of electric field and electric potential. And oh, this doesn't finish this one. I was drawing the electric field due to a parallel plate capacitor. Um, and then talk about the relationship between the field and the potential, and then talk about what we're going to do next and what I did not include. So let's start with some of the very basics. The magnitude of the electric field due to a point charge is K Q over R squared. That's the magnitude. If you write it as a vector, it would actually be like this. E equals K Q R hat over the magnitude of R squared. And that's important because when we want to calculate the electric field due to multiple things, we need to treat it as a vector. So in this expression, K is 9 times 10 to the ninth newtons meters squared per coulomb squared. And coulomb is a unit of charge. So this is just a universal constant for the electric interaction. Oh, I guess I should also say that the electric field is defined as the electric force divided by the charge. So if I take a little test charge and put it right there, and I calculate the force on it, and then divide by that charge, I get the electric field. So it's the force per unit charge. I guess I should say up here the magnitude of the electric field due to a parallel plate capacitor is constant inside, and it's equal to Q over epsilon naught A, where this is equal, K is equal to 1 over 4 pi epsilon naught. So that's just a constant. Okay, and A is the area of the plate, and Q is the charge on one of the plates. Okay, so that's the electric field, and we also did, I guess we should say this, if I have two charges, the electric field E is equal to E1, let's call this 1, 2, plus E2, so that we have superposition of electric fields. So if I want to find the electric field at this location right here, which would actually be that way and that way, it'd be kind of like this, I guess. It would be the sum of this electric field due to this charge plus the electric field due to this charge at that point. And so some of these situations it gets kind of complicated, and it's best just to use the a numerical calculation or Python calculation to do that. Yeah, that's the electric field. Now, what if I do this? What if I take a charge right here and I want to bring it into infinity, from infinity to some location a distance r away? Well, in that case, I'm going to have to push on it with the force because there's an electric force pushing it apart, and you can't even see that. I'm going to have to push on it with some force to get it down here. That means I'm going to have to do work. So if I do work on the particle to move it here, I could also say there's a change in electric potential energy up here. So the change in electric potential energy is related to work. So you always have to have a starting and an ending point. Okay, so we define electric potential energy for a constant electric field. Delta U electric for a constant electric field is negative E delta R, that is dot delta R, that's good, where that's the dot product. Or you could write this as negative the magnitude of E times the magnitude of delta R times cosine of theta, where theta is the angle between the electric field and the way you're moving. If you try to do this for a point charge, you can't because the electric field is not constant, so you'd have to integrate. I did this numerically, and we get the potential. Oh, the change in electric potential is equal to the change in electric. This is Q. This is force delta R. Q is the change in electric potential energy per unit charge. So it just takes out the charge, and this is in units of volts. The electric potential for a point charge is equal to K Q over R. This is with respect to infinity. Also, very important, this is a scalar. This is not a vector. So we do not have to, it's a scalar because this is calculating the work per unit charge, essentially, from infinity to some point r, and work is a scalar. Superposition still works. If I have 2-point charges, the potential is just the sum of the potentials. But still, we really want to deal with delta V. Delta V, in this case, one of the points is at infinity. Okay, now, so this is the relationship between the change in potential and the electric field. But it turns out that if I know the electric field, I can find the potential. But it turns out it works the other way too. I can say this. So if I know how the electric potential is changing with respect to x, I can find the x component of the electric field. And then I could do the same thing in the y direction. That's a y. See how the potential changes with y, and that'd give me the y component. And then you can do the same thing with z. So that's the key there. These are the two key relationships so far. The definition of the change in potential, the definition of the electric field with respect to potential. They're not the same thing. Okay. And so now we can use the ideas of both electric field and electric potential, and we're going to do circuits. Now, you may do some other things in physics that I'm not going to do. It may something like this. It's a great problem, but I'm just not going to do it. Here's a rod with uniform charge on it. What's the electric field right here? That's a great question, okay? But in order to do this, you have to break this rod into a whole bunch of little pieces and use superposition principle. And you end up having to do an integration with calculus. And I don't want to do this. This is an algebra-based course. I'm making this for an algebra-based course. And I have to write it out because that way it's true. Okay. You can do this numerically by breaking this into, let's say, 20 pieces, and then it's adding up the electric fields to 20 pieces. That's actually not too terribly difficult, but I'm not going to really focus on that. I want to focus on the bigger issues. What is the electric field? Later, what is the magnetic field? We're going to go into circuits because that's a very good application of electric fields and electric potential, but these other things we're just not going to do. Another thing we're not going to do right now is things like what's the electric field due to some other charge distribution. We have like a disk. We have the parallel plate capacitor. I did that one. A ring. These are all great problems. I'm just not going to do them because you have to use calculus to get that answer. Okay, so that's going to be it for chapter 2. The next chapter, I think we're going to go into, I'm going to do electric circuits. So I will see you there.